Okay, I want to take a look at, now that we've derived the equation for I, we want to take a look at the plot of this function. So if you plot I versus omega, get a function that somewhat looks like this. And if we plot the power as a function of omega, we get a similar shape. It's narrower because the power is I squared r. In fact, we can talk about average. And so we can call this IRMS. Now the width of this graph at half the maximum is related to the quality of the circuit. Okay, if you remember, the quality of the circuit is omega naught L over R. For this graph, it's also equal to omega over delta omega. That's not the case here because the width is different. So Q at omega naught is omega naught L over R, which is omega over delta omega. So let me write these. Let me write this down here because I'm going to need to erase the board here. Remember, this is from the power versus omega graph. But what if I'm given this graph? How can I get the Q out of it? How is the full width of half maximum? So what does that mean? What does the full width of half maximum is? If this is I max and this is I max over 2, you see that there are two frequencies at which you get half the maximum current. We'll call this omega 2, we'll call this omega 1. The difference between those two is delta omega. But this delta omega is going to be different from this one because it comes from a different graph. So how do I determine delta omega from this graph? And how do we relate it to the quality of the circuit? So I'm going to say delta omega, I'm going to call this delta omega sub p here and delta omega sub p here because this represents the full width at half maximum from the power curve, not from the current curve because it's going to be different. I want to find the two frequencies at which I get half the maximum. Okay, so let's go ahead and do that. So I need to erase my board. I need to find my eraser. When is the current maximized? It's maximized at the resonance frequency. Okay, so I max is V sub m omega naught over the square root of r squared omega naught squared plus 0. So this ends up being V sub m over r. Which makes sense, right? Because the reactances cancel out. So what is omega at half the max? Well, I'd say 1/2 I max is V sub m omega, which have to be determined. So these are the two frequencies at which the current is 1/2 the maximum value. So how do I solve for these two frequencies? Well, I'm going to take the ratio of 1/2 I max to I max. Okay, or you can take this term and substitute it over here, either way. Okay. So I take 1/2 I max over I max. So that's going to give me V sub m omega over the square root of r squared omega squared plus L squared times omega squared minus omega naught squared, the quantity squared, and then divided by V sub m over r. Well, this and this cancel. And then I have 1 over r. Well, that's going to go back up here. So this is what I'm left with. And this whole thing is equal to 1/2. I'm going to square both sides. And then I'm going to cross multiply. I guess I'll have to erase this. So I'm going to have to cross multiply, which will give me r squared omega squared equals r squared omega squared plus L squared times omega squared minus omega naught squared squared. Okay. Then I'm going to move this term to the other side. That's going to make this a 3. I'm going to divide both sides by L. I'm going to divide both sides by L squared. And I get that. So let me move this over. Then I'm going to take the square root of both sides. And of course, when you take the square root, there's always 2 solutions. Okay, so I'm going to move this to the other side of the equation. Let's see what we get. So because I have to use the quadratic formula and this can be plus or minus, there's actually 4 solutions to this expression. But frequencies can only be positive, so 2 solutions will be positive, 2 will be negative. It's the positive solutions that I want. I just use the quadratic formula for this. So for me to find the 2 frequencies that satisfy this, I use the quadratic formula, so it's minus b plus or minus the square root of this guy squared plus 4 omega naught over 2. Two of the solutions are positive and 2 are negative. So omega 1, let me take one of the positive solutions. One of the positive solutions is when this term is positive and this term is positive. Okay, so let me continue. I'm going to let me write this expression here. And anyway, let me continue. Okay, that's one of the solutions. Now the other solution is the case when this is negative and this is positive. So I'm going to get minus the square root of 3 r over L plus Now, if you take the difference, if you take this minus this, and I have these numbers, the numbers swapped. I should have called this omega 2 and this omega 1. Maybe I should do that. If I take omega 2 minus omega 1, that's delta omega for the current graph, and that's going to give me the square root of 3 r over L. Now, let's go back to our equation for Q. Q is omega naught L over R. Remember, that comes from the fact that it's 2 pi times the maximum energy per cycle divided by the energy loss per cycle. At resonance. Okay, so that's where this comes from. So I want to take omega naught over delta omega sub I, which is going to be omega naught over this expression. And this is going to give me omega naught L over the square root of 3 times R. So if I take the square root of 3 times omega naught over delta omega sub I, that's going to give me Q. So, we can say Q equals omega naught L over R, which is equal to omega naught over delta omega from the power graph, which is equal to the square root of 3 omega naught over delta omega for the current graph. That's why I have the I here. This is the current as a function of, this comes from the current as a function of omega, this comes from the power as a function of omega. And you have a question like this on your lab. That's why I went through this.